We continue our lecture still on 1D problems. Now we would like to see if we have been loaded with different type of loadings. In general, it can be several type of loading can be acted on 1D bar problems. But in this course, we just focus on three type of loading, which is the body force due to its own weight due to gravity. The second one is a traction force. Okay, then the last one is a point load. For traction force, initially it was a force, for example, like frictional force, surface shear, or the drag that we convert into Newton meter units. Okay, by multiply with the perimeter. Okay, and the last one is the point load. Point load, like exactly like we did in the previous example. Okay, let's look on the example how we going to solve the problem by using different type of loading. Okay, example, determine the unknown degree of freedom if bar are made from aluminium E 73 Pascal with density 2800 kilogram per meter cube. So please take note that in this example, the density value is given to us, meaning that we have to consider the weight of the bar in our calculation. Okay, so continue. Bar A has been loaded with a point load 10 kilonewton. Okay, and at the same time, both bars are also having surface shear 100 newton per meter at both sides of the bars. Okay, so here is our example. Okay, so we have two bars made from aluminium, the same material, but having different cross section. One is cross section 1 meter, the other bar having cross section 0.5 meter square. And please take note our axis X in this direction, okay, positive in X direction towards downward. And what will be our first step? So remember, our first step is to create the nodes and elements. So elements, and then also we have to determine the degree of freedom. So by using the technique that I have shown to you before, okay, we have to create the nodes at any important points that happen on the structure, okay, or within the structure. For example, node 1. Okay, so we create node 1 at this point because he's the beginning of the structure, and at the same time it's been having a fixed joint. Okay, that's why we take into account this node 1. And then node 2, at the point where the point load has been loaded. Okay, of course we want to take into account this load into our calculations. That's why we have to create node at this point. And then the third node will be at the border between two bar. Okay, of course we have to take into account these changes in our system. And the last one should be the end of the structure. Okay, the limit of our calculation. So we transform this node into elements. So element 1 is between node 1 and node 2. Element 2 between node 2 and node 3. And element 3 is between node 3 and node 4. Okay. Next step, we have to determine the degree of freedom. Okay. Please take note at node 1 is having a fixed joint. Okay. When it's fixed joint, meaning that node 1 cannot move. Okay. It's stuck. So U1 equal to 0. While for node 2, okay, node 2 is a free. Okay, at node 2, it doesn't have any support or any joints and so on. So meaning that it's free to move, okay, in X directions. Okay, positive or negative, we will look after this. Okay, so U2 is unknown. Similarly, for U3, U3 also free. Okay, it doesn't have any support, any constraint. Okay, that prevent it from moving. So it's also free to move. Okay, so U3 also unknown. And the last one is U4. Again, it's also a free end. Okay, so meaning that it's free to move. Okay, it's free to move in X direction. So we have U4. So in general, we have 3 elements and 3 degree of freedom, which is U2, U3, and U4. The next step, okay, after determine the degree of freedom, determine the number of elements and nodes and so on. Next, we have to calculate the stiffness matrix for each element by using this equation. Okay, so we can solve for each element. For example, element K1, the E is 70. A is 1 meter square, element 1. E is 70 gigapascal, and L1 is equal to 1 meter. Then we obtain this K matrix. Okay, the same thing for element 2, where A is 1 meter square. Okay, it's coming from this, still in, we're talking about this bar. Okay, we're talking about this bar. So the A is still 1 meter. E is constant, 70 gigapascal. And the L, okay, L is 1 meter for element 2. And the last one, element 3. So now element 3, okay, is about the second bar. It's a bar, okay, bar for B. Okay, so in this bar, the area is 0.5. Okay, so for element 3, the A is 0.5, E still the same, 70 gigapascal, and L, okay, still similar, 1 meter. So we obtain this K matrix for element 3. So K1, K2, K3 has been solved. The next step should be the formation of global stiffness matrix. Okay, so by using the same technique that I have shown to you, so next step we can obtain the global stiffness matrix. Okay, remember the first one here is coming from, here from K1. Okay, and next step, this one is coming from element 2. And the last one is coming from element 3. At this intercept, okay, we have to add. Okay, we need to get the summation. Okay, we need to get the summation. And the final global stiffness matrix will look like this. Okay, and please take note, the stiffness matrix should be a symmetrical matrix, meaning that it will be symmetrical. If here is negative 70, here should be negative 70. Okay, here looks here. Should be the same. It should be symmetry. Here is the line of symmetry. So it should be identical. Okay, all the K matrix should be identical. It should be a symmetrical matrix. Okay. So once we solve the global stiffness matrix, okay, the next step is to determine or to identify the forces, the loads that apply on our system. Okay, we should go one by one. We know that in this system, we have the body force, we've been acted with the traction force, and at the same time with the point load. Okay, so let's consider the first type of loading, which is body force, by using this equation. Okay, by using this equation. Okay, and it always based on element. Okay, check here. Here always check based on elements. So for element 1, okay, element 1, remember still bar A. The A is 1 meter. Okay, L1 still 1 meter. Okay, and then the force here, we're having density. Density is Newton. It's given by kilogram per meter cube. So we have to convert into Newton. To convert into Newton, we just need to multiply with the gravity. Okay, so that we will obtain Newton per meter cube. So by using this equation, okay, so we can solve for body force element 1. Then we obtain this value. Take note that element 1 is between U1 and U2. Similarly, we do for element 2. Okay, element 2, the A element 2, we are talking about bar A, so still similar, 1 meter. The L also 1 meter. And the body force should be the same because both material still under the same bar, so should be the same weight. Okay, and then we apply this equation, and we obtain this value. And take note that element 2 is between U2 and U3. And for element 3, now we're talking about this bar, element 3 in this bar. So the A is now 0.5. L still the same, is 1 meter. And density is still the same as both bars are made from aluminium. Okay, then we obtain the body force for element 3 here. And element 3 is between U3 and U4. So next step, we will have to assemble this body force to get the global body force metric for the system. So F1, look here, we take according to this node. Okay, so in this case U1 we have this value, so we replace here U1. And then U2 we have this value coming from this one, U2 from element 1, so we have this one. And then in element 2, again, we have U2 here. So that's why we plus here, U2. And then for U3, and coming from element 2, we have U3. Okay, U3, so we have it here. And in element 3, we also have U3. Okay, so that's why we add here U3, coming from element 3. And the last one is U4. So in this case, U4 only at element 3. Okay, so that's why we replace here U4. Okay, only in between that we need to get the summation, because this node, for example, node 2 and node 3, okay, they are located at both elements. Okay, for example, node 2 at element 1 also have U2, at element 2 also we have U2. Similarly for U3. At element 2 we have U3, at element 3 we have U3. That's why we have two value. So, and then the next step just to get the summation. Okay, and then always write this notation for your own reference. Okay, so we need that at each node, this is the body force that acted at the node that we have created. The next step, okay, to consider the traction force. The traction force is given by this formula, where this is the T is the traction value, L is the length of the element, okay, and 2 here is just a constant. So consider element 1. Okay, element 1, T will be the same. Okay, we are having the same traction force. Okay, traction force along the sides is the same value, 100. So it should be constant. So we have 100 here from the T. L, element 1, L1 for element 1 is 1 meter. Then we replace this value that we obtain, the traction force for element 1. And please note this notation, U1 and U2, element 1. Similarly for element 2, okay, the T still the same, 100. And the L for element 2, okay, L for element 2 still 1 meter. And then we calculate, then we obtain 50 and 50 for element U2 and U3. Okay, for node U2 and U3. Remember, element 2 is between U2 and U3. The last one, for element 3, okay, the traction force are still the same, which is 100. So we have 100 here. The length for element 3 is 1 meter, still the same. Okay, then we obtain this value, and node for element 3 is between U3 and U4. The next step will be the same. We have to get the summation of this traction force in order to form the global traction force acting on the system. So we go node by node. For example, we have U1. So U1 only having at element 1, 50. But U2, we have both at U1, at element 1 and at element 2. Okay, that's why we have 2 here. 50 plus 50. Similarly, for U3, we have U3 at element 2 and we also have U3 at element 3 here. So 2 times. So that's why we add here. 50 plus 50. And the last one, U4, we only have U4 at element 3. That's why we only have one value here, 50. And I get the summation. So here is the global traction force that acting on our system at the node that we have created. The next step is to consider the point load. Okay, the point load. Okay, just looking to our diagram. Okay, at P1 here, we don't have any point load. Okay, we don't have any point load acting on node 1. At point 2, yes, we have 10 kilonewton. Okay, 10 kilonewton. At node 3, okay, check at node 3, again, we don't have any point load. And at node 4, we also don't have any point load. So only at node 2, 10 kilonewton. Alright, and put this notation for your own reference. Once we have solved the body force, the traction force, and the point load for the whole system, now we need to get the summation of the forces, or the total forces acting on our system. So the total load of forces, okay, F is equal to the body force plus the traction force plus the point load. So recall the body force, okay, that one, the one that we have calculated, the traction force and the point load. So you just need to add according to row. Okay, according to row, meaning that the first row is for U1. So you just need to add all this value for U1. Okay, for U2 is this value according to the row. Okay, so when we plus, okay, when we plus, so we have the total force at node 1, node 2, node 3, and node 4. Okay, and please take note, in our system, node 1 is a fixed joint. Okay, node 1 is a fixed joint, meaning that at node 1, we're going to have a reaction force. Don't forget this. Okay, so that we're going to have a reaction force at node 1. Please add this reaction force in our equations. Okay, so once we have all the total loads, the next step is to obtain the system linear equation given by the formula F equal to KU. So we replace the matrix F with the global total force of the system. Okay, and then the K matrix from the global stiffness matrix, and U is given by the global unknown in our system. The next step, okay, is to check the boundary condition or to apply the boundary condition. In this example, we only have one boundary condition, which is U1 equal to 0. Okay, and remember, each row and each column is dedicated to its particular unknowns. Okay, meaning that row 1 and column 1 is dedicated to unknown U1. Okay, row 2 and column 2 dedicated to unknown U2, and so on. So in this case, U1 is already known. So once it's already known, meaning that the row 1 and column 1 is no more useful for us. Thus, we can eliminate the row 1 and column 1. So we eliminate column 1 and row 1. Then we obtain the reduced system linear equation so that we can solve the unknowns. Okay, so you have 3 times 3. So by using the calculator, okay, you have the function mode equation with 3 unknowns, and you can solve the displacement. And then we obtain all the value is positive. Yes, because we only have one direction of loads, okay, which is going downward. So our answer should be all positive because we assume the x direction is moving downward. Once we solve the displacement, we can use this value to determine the strain, stress, or the reaction force of the system. For example, we would like to calculate the reaction force at node 1. Remember, node 1, the respective row is row 1. Okay, so go back to row 1, or easily you know that the one that we eliminate, it will create the reactions. So we're looking at row 1, so here we have the RF1. That's why I always ask you to include this reaction into our matrix, so that later on when you want to calculate reaction force, it's easy for you to have the equations. So by referring to this row, okay, take it out. So we have this value on the left side, okay, and on the right side we have 10 power 9 times here 70 times U1. Just look on the above notation here, minus 70 times U2, okay, and the rest is 0. Okay, the rest is 0. And then we know that U1 is 0. So basically this term can be eliminated. Okay, only left this one, and you have to bring this constant value to the right side, so that we can solve the RF1, okay, by using the U2 coming from this value, the one that we have obtained, okay. Then you can solve for reaction force at node 1. Next, you can calculate the strain for element 2, for example. Okay, for element 2, so the equation will be dedicated to node for element 2, for meaning that the L will be L2, element 2. And the respective nodes for element 2 is node 2 and node 3. That's why we are using U2 and U3. So by replacing this value, okay, then we can solve for strain. And of course, once we solve the strain, then we can solve the stress by using the Hooke's law. Okay, so stress at element 2 just multiply with the modulus Young. Okay, in this case, the modulus Young is constant, which is 70 gigapascal. So multiply with 70 gigapascal with the strain 2, then we obtain the stress.